The Canary Islands are a favourite holiday venue for Northern Europeans seeking some winter sunshine. But the archipelago is a classic example of ocean island volcanism, situated far from an active tectonic plate boundary. For the Canaries, they lie thousands of kilometres away from the mid-Atlantic ridge, the active constructive plate boundary. So they are intraplate volcanoes, built on much older oceanic crust, and are the site of a long-lived mantle hotspot or plume, active for over 20 million years. So here they are. We'll visit two islands, Tenerife and Lanzarote, to look at the volcanic structures, landscapes, and the intraplate tectonics responsible for them. Welcome to the Canaries. This is the island of Tenerife, and it's one of the islands, and they're all volcanic. Really spectacular volcanic geology, and it's really worth getting away from the beaches and swimming pools to find out about it. Let's see what we can find as we scoop around. Famously, Tenerife holds the mountain peak of Teide, the highest point in Spain, and indeed the highest point on any Atlantic island. The Teide Massif is the active centre of the Tenerife volcanic edifice, but is only the younger part of a much longer history. The island is a composite shield volcano. Let's see what makes up this geology on the ground. The flanks of the shield volcano are incised by deep ravines that reveal layer upon layer, chiefly of pyroclastics, ash layer upon ash layer. Collectively, they chart hundreds of ancient eruptions. So, these ashes are actually welded. So pyroclastic flows that have come down the side of the old shield volcano, building up layer on layer. So really energetic and violent eruptions building up the original shield. It's not just pyroclastics. They're interlaid with basaltic flows, seen here as collapsed lava tubes in a road section. Well, what about the internal structure of the shield volcano? Well, this is really neat. The shrine actually is marking a well. It's not really a well, it's a tunnel that goes in, because the way in which people here get their water supply, back in ancient times certainly, was to put these tunnels in and, as they put it, mine the water. So this is a spring that extracts water from the inclined layering on the side of the main shield volcano. So Tenerife is riddled with these water galleries, some many kilometres long, and these reveal some of the roots of the volcano. Now, the oldest rocks outcrop are here, and along with those encountered in the water galleries, show that the shield volcano dates back to nearly 12 million years ago. Neighbouring La Gomera is another shield volcano. But Tenerife is made of more than just the central shield. Two others lie on its edges, younger than the older parts of the central shield. Let's visit the northern one, partly preserved on the Anaga Peninsula. So we're leaving the Teide Massif behind in the clouds. The Anaga forests are a very different landscape. Villages cling to the sides of deep-cut valleys. carved out of layered basalts and pyroclastics. There in the distance is the next shield volcano, the islands of Gran Canaria. In the northwest of Tenerife is another dissected shield volcano, named after the Teno headland. Although not covered by forest like Anaga, it too is heavily dissected, exposing thick volcanic successions. These landscapes show how readily these old shield volcanoes are eroded by rain and rivers, but also by the sea. The islands only preserve remnants of the volcanic structures. But there have been more violent landscape processes in play here. Look at the shape of the central shield. It's missing a bite. Let's find the rest of it. Well, if we step back, we can add information from seabed surveys that reveal vast submarine landslide deposits, a record of catastrophic collapses that have swept tsunamis not only around the Canaries but across the wide Atlantic. But historical eruptions for Teide continue to build out this flank of the island, adding instability for future vast landslips. Let's return to the high country around Teide. So this is pretty neat. We're in the heart of the Caldera and these old volcanic complexes here. These green rocks are ash, and here we've got a rather spectacular inclined sheet cutting across. Let's look at the margin up here. So we look on this margin to the inclined sheet with the ash that I'm stood on here. The ash has been eroded away and we're seeing the edge of the inclined sheet with all this fantastic fabric. So we can use this to see that the magma in the inclined sheet has been intruded like this, more or less in the dip direction, almost like it's a fault. So these intrusions will have fed surface eruptions. These dramatic towers reveal volcanic plumbing systems and make for interesting challenges for rock climbers. They're climbing on columnar jointing. If we look at the sides of the towers, we can see these columns lie side on. They form subperpendicular to the margins of intrusions, as they cool, and the intrusion margins were very steep, looking almost like a pile of children's building blocks. Okay, so much for the old caldera walls. Let's look at some of the young basalt flows here. So this is inside the rim of the main caldera of Tenerife. It's rather old because the main peak up there of Teide is much younger and sits inside this old caldera, and younger still is the cone on the left, and you can see these black younger lavas that have come down. They came in at the end of the 18th century, so all this black ground in front, much younger still. Really fantastic history of volcanic activity here. Anyway, let's continue along and get another view. So we can see really nicely here the flows coming out of that vent that's not quite on the crest, down from the crest of the main volcanic edifice, pouring lava down, and you can actually see successive flows by the way in which the weatherings occurred on top, the most recent being that dark black material over there. And it's all banked up against the side of the old Caldera wall down there, where the pale rocks, which are ash of the old Caldera, down there at the bottom. Really nice igneous geology. So I'm sat here on the floor of the old Caldera. It's a really nice pahoe or ropey lava, really runny basalt that's filled the floor of the Caldera, but it's overrun by the rough basalts that have come from the vents. That black rock up there is part of the late 18th century eruption that's backfilling the Caldera today. On Google Earth, we can see the lobes along the edge of the youngest black basalt flows, trying to blanket the older brown weathering ones below. But the main part of the young flow, which ran here from left to right, has large-scale ropey textures, folds in the solidified crust of the flow, rucked up as pressure ridges as the lava flowed onto the old Caldera floor. Really dramatic structures. Well, that's a quick synopsis of the geology of Tenerife, a massive shield volcano that's remained active into really modern times. Well, let's see a different style of volcanism now and switch islands. So it's off to the island of Lanzarote. Lanzarote lies over 100 kilometres northeast of Tenerife and, along with neighbouring Fuerteventura, contains the oldest rocks of the Canaries. The ages of these volcanic islands get younger from east to west. Migrating volcanism is expected when plates move over a deep mantle plume. So in this, the plume or hotspot is fixed below and the African plate moves slowly eastwards. So volcanism initiates later in the western islands. But once started, volcanism continues. To see how the later volcanism is expressed, let's go back to the ground. Now, Teide on Tenerife has no equal on Lanzarote. And without the high ground, Lanzarote isn't such a weather magnet. It's much more arid than Tenerife. Let's head up to the northwest of the island, well away from the main tourist complexes. On the far side of the bay is a dramatic escarpment, facing out into the Atlantic. It's the eroded edge of the old shield volcanic foundations of the island. As on Tenerife, this old shield edifice is being actively eroded. But in front of it, there are younger volcanics. But it's not the old shield that provides Lanzarote's volcanic highlights. It's the young and historic volcanism. Seen on Google Earth, black basalt flows cover over a quarter of the island, and they're pretty dramatic on the ground. These lavas erupted over just a few years in the 1730s, blanketing what was at the time rich farming land with blocky, vesicular basalt. So these basalts form the centrepiece of a national park. And Lanzarote itself is a geopark, and the community here have spent a lot of time telling the story of its volcanic geology. The visitor centre for Timanfaya is a wonderful exhibition of geology and landscape with 3D models of volcanic structures. But let's get outside and see the real thing. Even on a quiet winter weekend, people come to explore this wild landscape. Me too. Cinder cones poke out, not quite swamped by the young basalt. So let's go off a cinder cone. It's a bit of a trek through this lunar landscape to where the basalt lavas have flowed in between two older cinder cones. Eventually, the trail leads up onto, if not easier, certainly smoother terrain. So on the flank of this cone, you see the later lava flowing in the gap between this cone and the next one along, just pouring through, making that huge lava field. As the name suggests, the cinder cone isn't made of lava, but of cinder, gravelly ash, with large volcanic bombs, all of which were thrown out of the crater. And the crater rim makes for a great viewpoint. Not only for the structure of the cone, but also of the surrounding countryside. So how are these cones organised? Well, let's step back and have a look on Google Earth. These cinder cones, part of the landscape that predate the basalt flows, line up. What about the ones that fed the 18th century black basalt lava flows? They too line up along volcanic corridors. So even though these cones are point to eruption, they line up, well, they line, so they're fed by fissures, and in the crust that will be represented by dikes feeding magma up along plains that then come out as a few point sources represented by these volcanic cones. We can get an idea of the volcanic plumbing system in the crust from geophysical data, in this case by modelling gravity anomalies. And these reveal a deep conduit of magma that feeds shallower magma chambers in the near subsurface, and these chambers are lined up as the crust rifts apart. And on a large scale, the same pattern occurs. Lanzarote lines up with Fuerteventura and the Concepcion Bank, a former volcanic island eroded down by the sea. Collectively, these form the East Canary Ridge, the crust splitting to allow volcanism to continue, albeit less voluminously than it did during the shield construction episodes. So, dramatic volcanic structures and landscapes across the islands. They initiated as shield volcanoes sourced from mantle melting at a plume. Volcanism, though, continues as the crust stretches and rifts. All of this geology is really accessible, and much is described on interpretational panels, making the Canaries a great destination for the volcanic geotourist. And for a geologist based in Northern Europe, it's a great place for a spot of wintertime extracurricular fieldwork.